Hello everybody and welcome to Physics Rich, your one-stop channel for the preparation of IIT JEE, Advanced, Main, NEET and also AP. So how are you doing? Done with fluid statics? I hope you are. Well, if you haven't, then please go back and watch the other lectures in this series. We have already completed fluid statics and we are going to start with fluid dynamics, the first lecture today. And guys, I'm not going to take this lecture into, I'm not going to take too many topics. I'm just going to build your understanding from the very scratch so that you have a better intuition about fluid dynamics and you understand nature more rather than just simply run behind, I want to apply more maths and I want to do more problems. Okay, that's not what we are going to do. We are going to understand physics of fluids better in this lecture. Guys, do you know why I named this channel Physics Rich? It was because of this absolutely great teacher whose name was Richard Feynman. Now, if you do not know about Richard Feynman, let me just tell you that he is widely considered arguably one of the best teachers of all times. All times. Because he developed so many techniques to teach. He used to say that you should try to explain everything that you try to understand. Because if you can explain it in the simplest possible words, then that means you understand it the best. And do you know what he said about fluid dynamics? He said that despite of fluid dynamics being a subject of classical physics, it's still the most important unsolved problem. So as we study fluid dynamics, you will learn about something called laminar flow and turbulent flow. And I will tell you what turbulence actually is. Turbulence is one of the most important unsolved problems inside of fluid dynamics. So my dear students, why did Feynman sir say something this profound? Well, he said one very important thing, and that was that classical physics. What is classical physics? Classical physics is, well, all the physics that came before modern physics. In modern physics, what we do is that we try to observe things, but the problem is that the things that we're observing are like really, really, really small, like electrons, perhaps even smaller things like subatomic particles. So we use light to observe these very small, tiny particles like electrons. But the problem is that light itself disturbs the position of whatever we are trying to observe. So our observation methods are not that effective. That gives us a lot of constraint in trying to understand what happens on a quantum level. So that's all modern physics. That and, well, general relativity, which Einstein came up with. That's not what we're talking about. We are talking about everything that happened before that, everything that was developed by, like, fathered by Newton and developed further by other great scientists like Euler, and you will learn about more scientists in this course like Poiseuille, and there are a lot of them. Okay, so point is that Feynman sir said that despite of this problem being from classical physics meaning that physics for which we already have the methods of observation. I mean, we have methods of observation, we can find out the mechanics of it, we can find out the mathematics of it, but we still don't know how it is that they behave. You guys have heard of Heisenberg, Werner Heisenberg, the great scientist? Yes, that guy. You know what he said? That when he's going to meet God, he's going to ask him, why general relativity and why turbulence? And he said that I probably am going to get the answer for why general relativity. But even God's not going to know why turbulence. So turbulence, that's why it becomes one of the most important unsolved problems of fluid mechanics. And that's what I'm going to tell you guys, that this is one of the most complex topics in engineering. When you go to your favorite institute, be it an IIT, be it an NIT, or wherever you go and you learn engineering, you will come across fluid mechanics, especially if you take mechanical engineering, or if you take civil engineering, or if you take chemical engineering. For these fluid mechanics is one of the most important things ever. I mean, you know where is it that fluid mechanics is working right now? In our breath. That's also a fluid phenomena. Fluid flows inside my nose and then comes outside my nose. That's breathing. Breathing is a fluid phenomena. Right from here to rocket science, there's fluid mechanics. A rocket ejects a huge amount of fluid, basically it ejects gas per unit time, and that causes a large amount of force on the rocket, and then the rocket has to go through a lot of fluid that causes fluid friction on it, drag force on it. So you see that the understanding of fluid mechanics, that's why it becomes a very, very important feature for an engineering aspirant. But then the medical students are going to ask me, sir, why us? Why do we need to study fluid mechanics? Guys, medical students, what's this? It's my arm. Probably has a lot of blood inside. I hope so. That blood is applying pressure on the vessels inside my body. That's called the blood pressure. You need to understand the mechanics of fluids to be able to understand blood pressure better. I mean, can you really say that you're a doctor, you don't understand what blood pressure is? Can't say that, right? Exactly like that. You cannot really say that I don't have any interest in fluid mechanics and yet I want to become an engineer. Never gonna happen. And that's the reason, guys. That's the reason why IIT, NTA, all of these people, they are certain that they will ask you questions on fluid mechanics, whether or not if you like it. Fluid dynamics is twice as important as fluid statics. They will definitely ask you questions on fluid dynamics if they don't ask you on statics. Definitely. So, shall we start? Shall we dive into what fluid dynamics is? Yes, of course, we should. So, my dear students, Feynman sir says that physics is less about equations and more about understanding nature. And in this lecture, I will try to explain to you types of flow where you will understand the nature of fluid flow. I will try to keep you away from mathematics as much as I can. I mean, of course, we will be doing some practice problems at the end of this lecture, and I'm sure you will enjoy that. You will enjoy learning that. But I will try my best for you guys to understand the basic nature of fluid flow. All right, because you know what? We often make this mistake that we start running behind solving problems. We look at a chapter and then sometimes students, they don't even read the theory of the chapter. You know what they do? They turn the pages. They will pick a nice book like Physics Galaxy, or they will pick a nice book like Cengage, and they will start turning the pages and they will not read the theory and they will just find the solved example. Oh, you know what, like this. Oh, that's how I approach the problems. They probably don't even understand what the theory is. They will straight off jump to learning how to solve questions. Not good. Not good, guys. Try to understand the theory. Have some patience. It's gonna be nice. Have some patience, learn the theory, and then go to the solved examples. You will understand the whole subject, the whole idea holistically, and you will be able to apply it much better when you do the problems. So, let's think of water flowing through a pipe. Well, this is a pipe. Let's make a pipe. And let's imagine water flowing through it. Okay. Now you see, we understand one thing, that flow means some fluid is going to come inside and some fluid is going to go outside. Okay. This is what flow means. But does it mean that fluid in motion is flow? Well, the answer is no. That's not what flow means. Fluid in motion is not flow. I mean, not all the time. I'll give you an example. You can take a container, like like I have my water bottle. Okay, this is a nice water bottle that I use every day to drink water from. I finish this bottle twice, keeps me hydrated. So if I push this over here, Do you think that this water inside is in motion? The answer is yes, it is in motion. Like if I take it like this, yes, it's in motion. But is it flowing? Is it flowing? No, it's not flowing. But if I open the bottle and I start drinking from it, is it flowing? Did it flow? Yes, it did flow. Now, you see, what is the difference between fluid in motion and fluid flow? Well, the difference is quite clear. And do you know what is that difference? The difference is that when fluid flows, some amount of fluid definitely crosses a certain area. Like if we are talking about this bottle, okay, and this is the opening of this bottle. This area, you see, water definitely crossed this area and went into me. All right. Now, did fluid cross an area moving like this? But some would say yes, it did. But can you say that as I keep observing the fluid for some small amount of time, a certain number of particles through this area moved in and a certain number of particles moved out? All right. If I tell you that this is an imaginary area over here, okay, there is, let's say, some imaginary area over here. Let's make an imaginary area over here. Okay, something like this. Some amount of fluid particles, they went inside, and some amount of fluid particles, they moved outside. And you might be very tempted to say, sir, it's the same amount of particles that went inside and the same amount of particles that went outside. Yes, I agree. I completely agree. My only point is, guys, that fluid in motion and fluid flow are not the same things. Please try to understand this first. When I'm saying fluid flow, there has to be a real or an imaginary area through which fluid particles cross. Okay, that's the understanding of what fluid flow really is. Can I say that water flows just because it has speed? Could there be motion without flow? Yes, when I take the bottle and I push it, there is motion, but there is no flow. Okay, just because water or any fluid has a certain velocity, you can't really say that there is flow. What is the sure shot way of saying that there is flow? That through a real or an imaginary area, some liquid particles have to be crossing. They have to be crossing. Now, you see that if I try to understand the flow of water through a pipe which has a varying cross-sectional area. By the way, what is a cross-sectional area? Cross-sectional area, well, it's just an exposed area that you get when you cut something. Okay, so let me give you an example. So this is my phone. This is my phone. Okay, now if I cut it, I don't want to. It's kind of expensive, but still, for science, let's do some sacrifice. If I cut it like this, what are you going to see? You're probably going to see something rectangular over here. All right, when you cut it, the area that gets exposed is the cross-sectional area. All right, this pen, you see this pen, if I cut it, again, I don't want to cut it, but if I do, then the area that gets exposed, that's the cross-sectional area. Okay, now if I have a pipe with varying cross-sectional area, what it means is that perhaps I have something like this. Perhaps I have something like this. Okay, so if I cut it here, then I will have a different cross-sectional area as compared to here. When I will have a different cross-sectional area compared to here, different cross-sectional area. So different places, if I cut them, I will be getting different cross-sectional areas. Is that right? I hope that makes sense. Now, you see, guys, a very important thing, a very important thing. if I have this pipe, okay, and I tell you that some 20 particles enter inside. Some 20 particles they enter. How many particles will leave? How many particles do you think will leave? Don't you think that 20 particles will leave? Unless, of course, there's some chemical reaction or some nuclear reaction. Maybe there's I don't know, something radioactive put inside and it is producing more particles. Nah, no, that's not what we are assuming. We are assuming a normal, regular situation. Okay, this pipe is not producing more particles. All right, it's like 20 particles of water are entering. So 20 particles of water will also leave, unless there is this water producing more particles, which is kind of not possible. I mean, think about it. If it was possible, then we would take 20 particles of petroleum entering from one side, 25 particles of petroleum leaving outside, and the pipe is producing more petroleum particles. Free petroleum particles. Yeah. All energy crisis solved in the world. Oh no. But if we have more oil, then probably some people will want it, and that's not nice. Okay. Some very bad people will want it. So let's not assume that happens. Okay, I'm actually glad that doesn't happen. Like only 20 particles that come inside, 20 particles leave. Thank God. If the 25 particles were leaving, God knows what will happen to the country. Okay. So why is this happening? Why is this happening? You should say, sir, this is common sense. Of course, this is common sense. What are you talking about? 20 particles will enter, 20 particles will leave. But you see, guys, don't you think so? That this is also conservation of mass. Conservation of mass. And it doesn't matter if the pipe looks like this or if the pipe looks like this. Come on. You got to help me here. If 20 particles enter over here, if 20 particles enter over here, don't you think that 20 particles will also leave over here? I mean, what has the area of cross section got to do with the number of particles entering and leaving? Right? That's what conservation of mass means. Now you see that this mass remains conserved is actually a constraint. What is a constraint? Well, constraint means that there is a rule that has been imposed upon you that you must follow, and the rule is given to you because there are certain things that cannot change. And the mass that is entering and the mass that is exiting will be equal because the mass remains conserved. This rule cannot be changed, right? That's what conservation of mass means. Now you see that from this idea, a very important concept follows. And that's called the equation of continuity, which is based upon the thing that we just discussed, based upon conservation of mass. It's based upon the conservation of mass in such a way that if certain number of particles enter from one side, the same number of particles will leave from the other side. But this is kind of easy to imagine in a pipe that has a uniform cross-sectional area. Okay, like a regular normal pipe, which if you cut becomes a cylinder. Okay, now assume that this thing is full of water. Okay, and water is also coming inside from here and going outside from here. All right, so this thing has like no space. It's like tightly packed. Okay, so you see what happens is that if let's say, you know what, we'll make that 1, 2, 3, 4, 5, 6, 7. We'll make 8 particles enter inside. Or shall we make more? 8 is fine. 8 is fine. 8 particles are entering from here. Over here, you will see that these 8 particles will also leave. Okay, these 8 particles will also leave. And however, if I have a pipe that looks like this, these 8 particles that enter from here, will they leave the same way, guys? Or will they leave like this? You see, there's a difference. There's a slight bit of difference which is happening in this case and in this case. See, these 8 particles were taking this much amount of space, okay, like they were taking some vertical amount of space and some horizontal amount of space, all right, and they were taking the same amount of vertical space and horizontal space over here. But what about here? You see, this vertical space that they are taking, this is the horizontal space they are taking, but here they are now taking more horizontal space and less vertical space. Okay, now you see, guys, imagine it this way, that let's say that there is a road, okay, and not a road exactly, like, okay, fine, imagine a pathway. But the thing is that the pathway becomes narrower towards the end, and it has a wider entrance and a narrow exit. Okay, and think about this pathway to be like perhaps an entrance to maybe a temple, okay, or maybe some other religious place, all right, any other religious place. So it has a smaller entrance, but it has a wider uh, exit, all right, or we can think of it like this, that let's say this is the temple, or well, basically whatever this is, I don't know what this is. This is a temple or something, okay, and the road sort of looks like this. The road sort of looks like this, okay, and there are people coming in from here. There are people coming in from here, okay, and every second you see 1, 2, 3, 4, 5, 6 people enter. There are 6 people that enter over here, all right. But these 6 people will also have to leave from here, correct? As these 6 people enter, 6 people should leave from here, all right. So these 6 people should leave from here. Who do you think would be walking fast? That's the question. These guys, or these guys? Who do you think would be walking fast? And the answer is that these guys would be walking faster. Because you see that they need to create this much space for these people to enter. Okay. This space that they will create has to be equal to this space through which these guys will enter. Okay. But because this space is oriented in such a way, okay, like you can say that this space is oriented in such a way that it has a narrower, it is narrower, which is why this space also becomes a longer. Okay, I hope you understand this idea. So this space is narrower and that's why longer. However, this space is it has less width. All right, it has less width. So this gives us the equation of continuity. What happens is that you've seen that, like when you have a pipe and through the pipe water is flowing, and then you close the mouth of the pipe, slightly close it, and then water goes really fast. Have you seen that? I'm sure you must have done that as you were kids. If you haven't done that, you're missing so much in life. It's fun. You should do that. So if I have a pipe, okay, and then I suddenly close the mouth of the pipe, I suddenly close the mouth of the pipe. Then what happens is that this region, this has some m mass entering and this also has some m mass exiting. Okay. Or rather, I should say, because the densities are equal, the density symbol is rho. So m by rho means that it has a v volume entering and this has a v volume exiting. So you can say that the in volume is equals to out volume. All right. But that is also happening in delta t amount of time. Like in delta t amount of time, whatever volume enters, that much volume only goes out. This is called the volume flow rate. Please note it down. The volume flow rate. How much volume is entering and how much volume is exiting is called the volume flow rate. And the volume flow rate is equal whenever the density is the same. Okay. So if during flow the density does not change, the volume flow rate remains constant. Okay, please note this down. If during flow the density does not change, the volume flow rate remains constant. Now you see that this volume flow rate remaining constant will give us the equation of continuity, and we are coming to that. I will tell you what that is. So we told that V in upon delta t is equals to V out. Okay. V in is equals to V out. Now, how much volume is entering in? How much volume is entering in? Is V out by delta t, by the way. Yeah. How much volume is entering in? Okay. Let's assume that this is the delta x in and this is the area of the first side of this side, and this volume which is going out is, well, delta x2. It is covering this much length. Okay. And this has an area A2. So the in volume is just area multiplied by this length, which is A1 delta x in, divide this with delta t, and that is A2 delta x out divided by delta t. You see that delta x in by delta t and this is delta x out by delta t is basically displacement per unit time. That gives us the velocity. So this is A₁v₁ and this is A₂v₂. This is the equation of continuity, which comes from the idea of conservation of mass, and basically this is due to constraint. There is a constraint that the material entering in and the material entering out will be the same, and because they will happen at two different areas, so whichever area is less, the material flowing out of there has to go faster. Okay, and that is the equation of continuity, my dear friends. All right. Now you see that the density does not change. I have written this as the density does not change. This sometimes is also called incompressible flow. Okay, this is also called incompressible flow. Please note it down. And you can also write it in this way, that for incompressible flow, the volume flow rate remains the same across all cross-sectional areas in a pipe. Okay. I hope that makes sense. So yeah, we learned a little bit about equation of continuity. If I have a situation like this, okay, let's take the velocity entering over here. Let's say this is V in and this is V out. Okay, I will take V in as 2 meters per second. Okay, it's like kind of fast. And this area, okay, this area in, I'm going to take this as 4 centimeter square. All right. And this area is 2 centimeter square. This is A2. So if I ask you what is the value of V out, then how will you proceed with this problem? Then the answer is very simple. Sir, I will just apply equation of continuity. Equation of continuity, which is A₁v₁ equals to A₂v₂. And then I will say that the area over here is 4 centimeters square. The velocity in is 2 meters per second. The other area is 2 centimeters square. And the velocity is what we need to find out, V2 or V out, right? This V2 and V out are the same. So V2 from here, this centimeter square will cancel the centimeter square, the 2 will cancel the 2, and I will get V2 as 4 meters per second. Okay, simply this. Some people will ask me, sir, do I need to convert this centimeter square into meter square? Because, well, you know, SI units, relax, not really required over here. Now, can you tell me why it is not required? Well, because the units are the same on both sides. If I would have given you 4 meters square over here and 2 centimeters square over here, then would you convert? Yes, that is when you would convert. Okay, so that is a very nice explanation of equation of continuity. Let's take a look over here. Now, you see, it's the same pipe, but I have cut it like this. I have cut it like this. So what is happening over here? Assume that this area is 4 centimeter square. All right. And the velocity over here is 2 meters per second. But because I have cut it like this, so this area becomes 6 centimeter square. I mean, you can think about it this way, like when you cut it sideways, the area should increase, no? And now the velocity over here, V out, is being asked. All right. Many students will be tempted to apply equation of continuity over here. And they will say that, oh, sir, it's kind of simple. We'll just apply equation of continuity. A₁v₁ equals to A₂v₂. And what is A₁? A₁ is 4 centimeters square. V1 is 2 meters per second. And this other area is 6 centimeters square. And we need to find out the velocity. And 4 times 2 is 8, 8 by 6. And oh my God, I got 4 by 3 meters per second. And you will look at 4 by 3 meters per second in one of the options. You will tick and you will get negative marks. But sir, didn't you just tell us that you have to apply equation of continuity over here in such kind of problems? Yes, guys, I did tell you, but I also told you that equation of continuity is more like a constrained equation, okay? It's more like conservation of mass. It's more like common sense, which children, students do not apply. Okay, and let me tell you why the equation of continuity cannot be applied in this way over here. So, here's the thing, guys. Let's try to understand this very nice, confusing problem one more time. So, second. Yeah. So, what is happening over here? Guys, think about it this way. Assume that some 1, 2, 3, 4, 5, 6, 7 particles I made over here. 7 particles they entered. Okay, let's take these particles and line them up over here. 1, 2, 3, 4, 5, 6, 7. Okay, let's line them up over here. These 7 have entered and these 7 want to leave. But what exactly is going to happen? This guy, yes, it will leave. But what about this guy? Will it leave? The answer is no, it will not. Instead, another particle that is over here will leave. Instead of this guy, another particle over here will leave. Instead of this guy, another particle over here, over here, over here, over here. And if you count in total 1, 2, 3, 4, 5, 6, exactly 7 guys will leave from this side. Which means the number of particles entering over here and number of particles going over here are the exact same, which is true in any case. But here you see that these particles can be arranged onto this cross section area as well. So our V out, okay, our V out in this question is nothing but V in, which is 2 meters per second, and that's our answer. Okay. So in a lot of books, you will find this explanation. And you will say that, and I'm taking this from like engineering books. You know what they do over there? They introduce a concept called flux. Okay. And they say that, okay, this velocity V over here, all right, and there is this area A over here. We will not take VA, or we will not take A₁v₁. You know what we will take? We will take AV, wait for it, cos theta. What is cos theta? What theta, sir? Okay, check this out, guys. So, are you going to be surprised if I tell you that area is a vector? Yes, it is. Area is actually a vector. You see that this area and this area, they are not pointing in the same direction. And how exactly do you understand that area is a vector? You look at this board, okay? This is an area. Do you know where is the direction of this area as defined by mathematics? It's directly towards you. This area is a vector whose direction is pointing towards you. Yeah, that's the direction of this area. And you know where else you've studied it? You've studied it in cross product, A cross B. I hope you remember A cross B. If this is A, this is B, then A cross B points upwards. And the parallelogram, which is enclosed between A and B vectors, is the area of that's the cross product. The area of the enclosed parallelogram is the cross product. So, and the cross product is, well, a vector product. So that is where we get the idea from. That area indeed is a vector. Okay. Now, where is the direction of this vector? This area, and that is over here. This is, let's say, A2. And the velocity direction will be over here, V. Let's call this V1, let's call this V2. So you know what the equation of continuity says? It says that the dot product of these two, as in A2V2 cos theta. Well, what theta? This theta. This theta. And what about the theta over here? What about the theta over here? You will say that, sir, this theta seems to be 180 degrees. V1 is over here, A is over here. This seems to be 180 degrees. So instead of this, I will write 180 degrees. And what is cos 180? Cos 180 is actually -1. So that means this is minus AV. Right? So these books, like good books like F.M. White and all these guys, you know how they put continuity equation? They say that the dot product over here, which is A2V2 cos theta over here, plus the dot product over here, which is minus AV, is going to be 0. That's how they put it. You understand? So A2V2 cos theta is equal to the volume flow rate. Very important concept, guys. Something on which JEE can easily trick you whenever it wants to. Okay. So this is how they put it. So they say that, okay, volume is entering inside. This is your pipe. This is the area. We will always take the area away from the pipe like this. So this is the area, this is the velocity. And that's why they have anti-parallel properties. And that's why cos 80, 180 is used over here. And then they said that, okay, volume in, volume out. That's why volume in will be taken as negative, volume out will be taken as positive. When you go to grade 12th, you will encounter a very similar idea in electrostatics, and that's called electric flux. And you will thank me in grade 12th that I taught you this today itself, because that time the concept will feel familiar and easy. Okay, so guys, this is how you will write for this question. But then you will say that, sir, I don't know the angle over here. I actually don't know the angle. But my dear students, do you even need to know? Do you even need to know? You don't need to know. You know why? I'll tell you why you don't need to know. Because he asked you what is this V2, right? He asked you what is this V2. And you are saying that this A₂v₂ cos theta is equals to A₁v₁, or you can write V2 A2 cos theta is equals to A₁v₁, correct? What is this A2 cos theta? What is this A2 cos theta? Think about it this, guys, that this A2 cos theta, I will remove this V2 over here. Okay, let's make a projection onto this side. This is A2 cos theta. You guys know a little bit of vectors, right? This is A2, this is A2 cos theta. And this seems to be in the direction of the flow itself, which means that this A2 cos theta is the cross-sectional area. And you see this A2 cos theta is the same thing as A1. So you can cancel this over here. And that's how we get V2 equals to V1. Okay? Very beautiful concept. And like I said, guys, physics is less about equations and more about the understanding. And what did we understand from here? We understood one very simple thing, that because the cross section of the pipe was constant, the speed with which fluid will flow in is the same speed with which fluid will flow out. Okay? To explain this, books like Bruce Munson and F.M. White will go into Reynolds transport theorem, and they will try to boggle you with a lot of maths. But no, that's not how it should be. Physics is more about understanding nature than about mathematics. Let's now understand one more question over here, in which I will expect that you will apply more common sense and more understanding of nature than simply do equations. So there is this situation of a Y-shaped pipe. In this Y-shaped pipe, you can think of it like this is like hot water, cold water, and this is your water in your shower. Okay, this is coming from your geyser or something. Okay, this is coming from your regular tap from the tank. Let's assign some values. This area is A1, okay, and I'm going to put A1 as 2 centimeters square, and it is coming with a velocity of 3 centimeters per second. It is slow, okay, and let's say this is area A2, and that is 4 centimeter square, okay, and it is coming in with a velocity of well, let's take 2 centimeters per second. Okay, I'm just assigning arbitrary value, guys. Okay, and this area A3 is 3.5 centimeter square, and what will be the velocity? That's the question. But you see, this is not one pipe, so you cannot apply A1v1 equals to A2v2. You cannot even apply A1v1 cos theta because there's no such cos theta over here. So what do? We apply common sense. Okay, volume in is equal to volume out. All right, where is the volume in? This is the volume in. And what is the volume out? This is the volume out. So guys, how much volume per unit time is coming in? volume in is happening here, and this is 3 times 2, 6 centimeter cube per second. See, centimeter square, centimeter cube. Multiply that. Plus, what about this one? 8 centimeter cube per second. Total 14 centimeter cube per second. What about this guy? What is the volume flow out? It will be 3.5 V3 centimeter cube per second. We will assume V3 to be in centimeter cube per centimeter per second. So we will just equal this with this. Okay. So what do you get? 14 centimeter cube per second is equals to 3.5 V3 centimeter cube per second. Khachak. V3 is 14 upon 3.5, which is 4 centimeters per second. Okay, so that's our answer, 4 centimeters per second. Now you see, we did not apply any formula over here, but we just understood this from our basic common sense and intuition. And some students will still ask me, sir, but what is the formula? What formula did you apply? Okay, fine, I'll give you the formula. A₁v₁ plus A₂v₂ equals to A₃v3. That's what I did. Okay. Just in case if you really want me to tell you what formula I applied, I did this. But more than the formula, I applied common sense. And what was the common sense? That the volume in is equal to the volume out. That's all. Okay. All right, guys. So that's what it is. Now, what is happening over here? Let's check out what is happening over here. You see that there is flow of water in and flow of water out. But this side, it's just like an open area, and this side has like n holes. Okay. So what is the volume in? Volume flow rate in. You know what? We should actually write it as V dot. The dot means volume flow in, which is the AV. So over here, that will be pi r square. Guys, do you know why pi r square is there? Pi r square because this is a circle. It's not an ellipse. Okay, it's a circle. Pi r square V. That should be equal to V dot out. What is V dot out? You can see V dot out is going to be whatever velocity it will come out. Okay, he's asking the exit velocity, right? So we will say that this is, let's call it V dash, okay, or VE. VE, E stands for exit, times N, and the small holes have a radius of small r, so pi small r square. So this is equal to this. What do I cancel? What do I cancel off? The khachak is so satisfying. So VE simply becomes r square V upon, what is this? N small r square. Easy peasy. Oh my God, such a simple question. Okay, let's move on. What is happening over here? Oh, this is a very, very repeated JEE question. This is J23, JEE 04, like many years ago. Okay. When I was in grade, what? 10th? No, 9th, something like that. So this piston is being pushed like this. Okay. This piston is being pushed like this. And assume that the area can be calculated using this radius capital R, and this has a radius of small r. Okay. And this is being pushed by a velocity of, let's say, u. And they will give you the value of u, they will give you the value of capital R, small r, everything. Apply equation of continuity. Simply, the speed of the water over here times the area, which will be pi r square u, should be equal to pi small r square v. Khachak. V equals to u times of r by r whole square. Easy. All right. You can see that this question has come repeatedly in many JEE exams. So simple. Okay. JEE mains. Little bit of study. Guys, little bit of study. You will crack JEE mains. What's happening over here? He's asking us dH by dt. Now these questions, they try to scare us by putting complex looking things like dH by dt. Oh, this is calculus. I will scare you. Doesn't work. You know how? Because in this question, he's most likely going to give you that the area of this exit, okay, and this, or basically this, they will be the same. Let's call this area small a. Small a v is the v dot out. What is v dot? V dot is the volume flow rate, okay, v dot out. Now that should be equal to, and he will also give you the area of this side, capital A times v of this, velocity of this water falling down. So A times V should be equal to small a times, oh, this is V, I've taken this V now. I'll take small v over here. Take small v over here, guys. Small v, okay. Take small v, and this is capital V. But here's the thing. You know what this V is? This V is dH by dt itself. So simple. So you will just write dH by dt times A equals to small a V and dH by dt. That's how becomes A by capital A small v. I have done a very good problem on this in the osmologist series. Head towards that and check out that problem in which we try to calculate how much time it will take to empty. If you find this to be very basic, you will find that to be very interesting. So the playlist is right there. All right. What about here? What's happening here, guys? Have you ever seen a tap being opened? If a tap is being opened, the fluid, the water that flows out of it, tries to become thinner and thinner and thinner, and suddenly it breaks. Okay, suddenly it breaks now. It breaks, let's say, over here. But why is it becoming thinner? Why? It's becoming thinner because basic physics, guys. Water flows down, gains speed. And because it gains speed, this velocity, let's say, V2, this let's say V1. So V2 will definitely be bigger than V1 because of gravity, because gravity has pulled it down. And that's why we can say that wherever the velocity is high, the area of cross section will be less. So you can say that A2 will be less than A1. So basically AV is constant. Some people also draw the graph of A versus V in this case. This is velocity, this is area, and then the graph looks like this. You can do that as well. It's a rectangular hyperbola. Larger the V, smaller the area. Easy. Now you see, well, how much time have we done? Okay, we have actually spent a decent amount of time trying to understand the equation of continuity. And guys, I think I will make another lecture in which I will explain to you everything about streamlines, laminar flow. I've written the definition over here, but I will explain it later, and turbulent flow. So guys, we will talk about the other aspects of fluid flow in the next lecture. We will also do this question, which again came in the very recent JEE exam. So we will do this as well. And until then, stay physics rich. I'll see you next time.